Hey, good morning. All right, so what we are going to cover today is red-black tree deletion. This will be the last topic that is covered on the exam that's going to be on Wednesday. So the exam review is posted and all the videos are up there as well. So you are welcome to use those in order to be able to study for your test. And it's going to be in the same type of format and the same way that we did exam one. The only difference is I'm going to have the papers stapled together so that way I can hand them out a lot faster than on exam one. Okay, so all right, so now let's delete these elements. So in the last lecture, we built this this red-black tree that's on the right. And we use this analogy of a modified B tree in order to be able to see how to perform balance. And so what we are going to do is we're first going to delete 11. So 11, this scenario is one of the easiest ones to address because we have a B tree node on the right here that happens to be, that will still have a value inside of it. We don't have to move anything here. So what's going to happen is if we delete 11, we're still going to be able to have all the balance in the red-black tree. So what will happen is that node will just go away, and we'll see that in the equivalent B tree, that this red 11 is just going to disappear. So now we're going to delete 14. Oh, sorry. Oh, okay. I don't know why it said delete 11. All right, so let's delete 14. And what's going to happen when we delete 14 is that it's going to move 11 up here. I apologize for not deleting that other slide. So 11 was initially here, 14 was here, and what's going to happen is 11 would move into the middle and become a black node. So we're going to see that 14 is going to move up, and 11 will replace it there. So in that case, it would be like we're grabbing the largest one on the left-hand side, and we have maintained the balance. So the next one we're going to do is we're going to delete 4. So first, what I want you to see when we delete 4, and let me make this a little bigger so that way it's visible to everybody. When we delete 4, what we're going to do is we're going to grab the largest element on the other side, and that will initially be 2, and 2 will move up and will initially be a red node. So it'll look like this. So here's how this would work. We have an empty node on the left. In the red-black tree definition, we would be saying here that this node has a null black node. Does everybody understand that? So the equivalent is we have this scenario here. In a B tree, what we would do is we would be doing that borrow from next and moving everything over in order to make this work. So what we're going to see is that we're going to move 2 down, like so. But how do we make sure that we keep track of everything? Well, what we're going to see is that we are going to perform this rotation to the left, just like we were doing with the B tree. The crucial part is we have to figure out what we're going to do here with 5. When this moves down, what's going to happen is 2 is going to become a black node because it's going to move here. And 6 is going to move up to here, so it's going to become red. Does everybody see that? 5, because we're doing borrow from previous, is going to be moved over here, and it's going to become a red node in that representation. So it's going to look like this. Does that make sense to everybody? Okay, next step. We are going to delete 8. So when we delete 8, 8 is the root. On the exam, when I do the B tree problem, you can bet that there will be 2 deletions. One of the deletions will be to delete the root node, and the other deletion will result in a large rotation to the left. And we'll see examples of this in lecture today. So here we see that I'm going to delete 8. And so the way this is going to work is when I delete 8, I'm going to take the largest value on the left-hand side and move it up. So in this case, it would become 7, right? Then this will become empty. And then we have this scenario here. So the way this will work is, let me go to the next slide, because the next slide we can move 7 up. And now we're going to perform a rotation. When we borrow from previous, because we have 2 elements over here, if this were in the B tree, what would end up happening is we would be moving this back down, like so. So 6 would come down, 5 would come up, and 2 would remain in place. So this, in this, in the red-black tree equivalent, we're now performing a rotation. We're going to lift 5 up and move 6 down. Does that make sense to everybody? We're going to go through another example together where we're going to interact, and I want to be able to pre-test and see how well you understand. So now we're going to delete 10. So 10 is a red node on the right-hand side, and we see it's in the middle. And the first step is we're going to grab the element that's largest on the left and move it up. So we see that 9 is moved up, and it's initially the same color. So now we have this scenario where we no longer have enough elements to maintain all of those nodes. So what's going to happen is, in the B tree representation, we would combine, move 9 down and combine 9 and 11, like so. Does everybody see that? So when it moves down, what we're seeing is that 9 becomes the black node. So to go back, when we combine 9 and 11, 9 is in the middle and 11's on the right-hand side. When we have this scenario here, we have a null node on the left. So now what we have to do is, this is essentially just recoloring. So in the red-black tree representation, what's going to happen is 9 is going to become black and 11 is going to become red. And now every single path to every single null pointer goes through 2 black nodes. So now let's delete 9. So I delete 9, I don't have anything on the left, so right is going to move up like so. Does everybody see that? And then the other one is going to delete 11. So this is the second scenario that I was telling you about on how to prepare for the exam. When I delete 11 here, you're going to see that I have no way to possibly balance it and maintain the 2 nodes to every path here. So as a result, I can't possibly borrow here because there's not enough space. Likewise, I don't have anything else on the right-hand side, which means that there's going to have to be some sort of rotation to be able to do this. So in order to make this work, I would have to do borrow, combine, and borrow. So in this case, in the B tree representation, I would combine these 2. But in order to make this work, I'd have to move 5 over. So now let's do that same step, but review it from a purely red-black tree example. In this particular case, what's going on is that we are going to rotate right, which means we're going to move 5 up like so, and 7 is going to become its right child. To maintain 6, 6 is going to have to move here, but now we're going to have 2 as its left child. So before we do any recoloring, 2 would be black, 5 would be red, 7 is still black, and 6 is now black. Right? So that's the way it was, that's the way it's going to be before we recolor. But now we're moving everything around, right? 2 is going to remain black. And so if we recolor the original grandchild, parent, and grandparent, what's going to happen is we're going to have the proper coloring. So we see that 5 and 7 are rotated like so, and 5 and 6 are recolored, and that's our new red-black tree. And then if I choose to delete 2, well, now 2 is going to be an empty B tree node on the left. And I delete 5, that moves 2 up. And now I have an empty tree, but this would be in the B tree representation, a borrow from next. So we're going to rotate. 6 is going to be moved up, 2 is going to be moved down, and all 3 are going to be black. So then what's going to happen is if I delete any of these values, we're going to have a situation where we're going to combine the nodes together. So in this case, I'm going to delete 2. So I'm deleting 2 on the left. That means I'm going to, that this particular node is going to be empty, right? And then what's going to happen is we have to combine these two, which means we're going to move 7 up. And in the representation, what's going to happen is 6 is going to remain black and 7 is going to become red. Then we move it up like so. And then finally, if we delete 6, 7 moves over, and then we delete 7, it becomes empty. So what I would like to do is I would like us as a class, but here on the exam review, I have these visualization links for Avl trees, B trees, and red-black trees, because those tend to be the 3 hardest for students to kind of work with. So what we're going to do is we're going to work together. We're going to pick numbers and insert, and our goal is to try to figure out how we can insert values to generate rotations and then delete values to generate rotations. Because if you can come up with problems like this to study on your own, that means that you have a really strong understanding of what's going on. So somebody just throw out a random, let's start, in fact, I'm going to also bring up the chat here. So what I want people to do, I want somebody to just throw out a random number. 4, very good. All right, so 4, if we start out with 4, okay, now I'm going to insert 39. So what is going to happen when I insert 39? 39 is just going to become the right child of 4, and it's going to be red. Okay, someone else. Okay, 12 and then, oh wow, that's amazing. Okay, so we're going to insert 12. So 12 is now going to become the left child of 39. So what I'm going to do is I'm going to press pause. Okay. So what do we think is going to happen here? What is this scenario? Yes. Hey, we're going to do a rotate left. And since we have a zigzag, which one is going to become the new root? 12, very good. So we're going to see that it's going to move here. It's going to perform that rotation. So when I presented in the lecture on Friday, we called this case 1, and it rotated it up, and we said it was a non-terminal case, right? So this brings us to case 2, which now brings us to that left rotation. And we're going to see that 12 and 4 are going to rotate. And then the last step is the original grandparent and the original parent of that step. In this case, those are 4 and 12, are going to be recolored. Hey, throw out another number. 18, very good. All right, so 18 is now going to become the left child of 39. So what do we think, what's the case that's going to happen here? Yes. Very good. And then what's the other thing that's going to happen? So I know why you stopped, because 12 is going to stay black, but out of a sense of consistency, just so we go through every step, what will happen to 12 first? Very good. All right, so the answer for those of you in the chat is that because the uncle 4 is red and the parent 39 is red, then we're going to change the colors of the parent and the grandparent. and the uncle. So we're going to see that 4 is going to become black, and 39 is going to become black, and 12 is going to become red. And now the last step was that case 0, where the root is going to become black. So now we have our balance. All right, next number. Someone in the chat this time. Someone not named Brandon in the chat. Throw out a random number for me. 27, very good. All right, so now we're going to do 27. And 27 is going to become the right child of 18. So what is this scenario? What do we do here? Okay, so then first let me give you a hint. What is the color of 27's uncle? Black. And why is it black? Yeah, exactly right, because all null pointers are defined as black. Raise 27 to be the parent of 18 and 39. So Tiani is correct as to what the whole step is going to be. So it's 2 steps in the actual algorithm. First, we are going to rotate 27 up to be the parent of 18. 18 will become its left child, and 27 will become the right child of 39. But what Tiani is suggesting is correct in the event that you're working on an exam you want to optimize. You would just be rotating. 27 would become the parent of 18 and 39. But then we rotate, and then we recolor the parent and grandparent prior to the rotation. And that's going to be 39 is going to become red, and 27 is going to become black. Okay, so when I ask you to pick the next number, I want you to think from a perspective of if you were writing an exam problem and what it is that you think I would want to evaluate of your knowledge. So what do you think, and based on where this tree is going, what kind of numbers would I be putting in at this point? What would be my goal? Yes, in fact. 45, very good. So you're picking up what I'm putting down here. So 45 is going to become the right child of 39. So to follow up with why you chose 45, what do you think I would be leading towards here? Exactly right, because what's going to happen is if we get 45, I'm eventually going to start piling up on the right in order to generate a rotation left. So we're going to get 45, and 45 is initially going to be the right child of 39. And so what is this case here? We've already encountered this particular case before. What do we think is going to happen here? And I'll give you a hint. What's the color of the uncle of 45? Okay, it's going to change color, so absolutely right. So in this case, because the uncle is red and because the parent is red, we're going to change the colors of the uncle, the parent, and the grandparent. Right? And so we would eventually recurse up and we would discover that at this particular stage that we have a correct red-black tree. And we leave it alone. So now to follow up on what was being said before, pick a number that you think I would probably try to pick again to make this problem work. What would be another number here I'd want to do? No, I'm trying to generate a rotation left. So how would I go about doing that? Yes. Let's pick 46. All right, so if we do 46, it's going to become the right child of 45. And so now I have a black uncle because it's null and a red parent of a red child. So what's going to happen here? What do you think is going to happen, specifically with 39, 45, and 46? Yes. We're going to have a little left rotation there. And so 45 is going to become the right child of 27, and 39 is going to become the left child of 45. And then what's the last thing I need to do here? Very good. I'm starting to hear more confidence. We're going to change the color of 45 and 39. So we still haven't produced this big rotation that I want to do yet. So what do you pick another number that I want to insert? 50. All right. Insert 50. So now we're going to go through here. So now this particular iteration is important because this puts in two key portions of the red-black tree. The first part is that it's local, right? So we have a local movement, and then we also are going to do a recursive aspect. So first, let's focus on this first local value. We have red uncle, red parent, black grandparent. What's going to happen here with 39, 45, and 46? Color change, very good. They're all going to change colors. And so that's the local part. So now we're going to recurse up, and where's the next place where we're going to encounter an issue? Very good, 27 and 45. And the reason why we're going to encounter an issue there is because we cannot have a red child of a red parent. So now what's going to happen here is we have a red child, 45, a red parent, 27, and a black uncle and a black grandparent. So what is going to happen here? I'll give you a hint. This is what I've been setting up to. Yes. Very good. So we're going to do a rotation of a left, and the crucial thing that you pointed out that's absolutely right is we also have to make sure that we move over 18. So 18 is going to become the right child of 12, and 27 is now going to become the root. And so what is the last step of this particular rotation? When we do that rotation where we have to rotate and we had a black uncle, black grandparent, red parent, what is the last step of that case? We called it case 2 in lecture. Recolor. So Tiani is very right. We're going to recolor 12 and 27 to make them red and black. Okay, so far so good. All right, so I've done several insertions. So now I would want to do 2 or 3 deletions on an exam. So what is the first thing first deletion you'd think I'd want to do here? Based on what I was saying a little earlier in lecture. Yes. Okay, let's delete 27. So very good. So one of the deletions will be a root. And so when I delete 27, what's the first thing that's going to happen? If I delete a node, what's the very first thing I do in any tree? Yeah, largest value from the left. And the largest value from the left in this case is 18. And Brandon has also said the correct thing, get the highest number from the left. What we're going to see is that 18 is moved up, right? So is this a valid tree? Is this a valid red-black tree? And if not, where is the problem? Yes, I'm sorry, I didn't see your hand up. Absolutely correct. We do not have, so you're absolutely right. We have to go through the same number of black nodes to every null in the tree. And in this case, this is invalid because we would have to go through 2. We only go through 1 to get to this one, and all the rest we have to go through 2. So in the previous step, what I'm going to do is I'm going to press previous, step back, So we move this up. And now what we would be doing in the B tree equivalent is doing a borrow from previous. And in this case, what's going to happen is we are going to recolor 12 and 4. Because 4 is previously the middle of the B tree node, but now 12 is, like so. And as a result, now we have a valid path to everything. So now if I delete 18, let's see what happens when we delete 18. I delete 18, what's going to happen is it's again going to get the largest value to the right and move it up. And then we still have that scenario where we're moving it over in the loop. So we're borrowing from next, and now 4 would be the middle of the B tree node, which means we're going to recolor 4, like so. Does everybody see that? So this is why I'm saying 3. Sometimes when I say I would do 3 deletions on an exam, because I would want to produce the scenario we're going to get here. So we're going to delete 12. If I delete, actually I will delete 4 because deleting 4 will give me the same thing and it's not a root. So if I delete 4, it's going to be gone. But now I would have a scenario in the B tree representation where I have an empty key and I have to borrow. So in this case, I would be rotating right. And so what do you think will be the final representation of the tree when I perform this rotation? Actually, let me ask in a better way. Let's work through this step by step. So what do you think is the first thing that's going to happen when I perform this rotation? What do you think the first thing you do? If you had this particular tree, you're almost home, you're almost done with the problem, what's the first step you would do? Someone give it a try. Anyone on the chat? What will you do here? We're all stuck. We're all going to fail Dr. Morrison's exam. Give it a try. What will happen? What's that? You're all like, oh, I don't want that to happen. So someone give me a good guess. Yes. Absolutely right. So the first step, I apologize for cutting you off. The very first step, 45 would become the new node. And then what's the next thing? Absolutely right. So here's what's going to happen. We are going to rotate such that we're going to rotate over. 45 is going to become the new node, the new root, and 12 is going to become the left child of 45, and then 39 is going to become the right child of 12. Does everybody see that? I'm happy to walk through it again if that's unclear. Does anybody on the chat want me to walk through that? Because that's a crucial portion. I will be evaluating. Yes. So let's go through this. So this is the step. So here's what was identified. We see that we have a null, which is a black node, right? So in this scenario, we have to consider what's going on here. This is the crucial portion. So in this case, we actually would have a B tree node here and a B tree node here. So we're actually performing a borrow from next. Now what's going to happen is 45 is going to be moved over, and so is 39. And what's going to happen is 45 is going to become the new root of the tree. 12 is going to be moved down. And then since 39 is between 45 and 12, and 45 is going to be pointing here, 12's right child is going to be 39. And so, I'm sorry. So what we're going to do is we're And in the animation, it puts out a new leaf, but just to make it clear that this is because it's a null child. We're going to rotate over. We're going to see that 45's right child is going to become 12, and 39's right child is going to become, 12's right child is going to become 39. So then that leaf goes away. So let's walk through this last step. So what would happen is we would recolor here. But now we have one last problem. Does everybody see what the last problem is? Where's this tree? Where's this particular tree violated? Yes, the left child of 12 is null. So what we're going to do is we are going to recolor these particular nodes, 12 and 39, and this will move up here. And now we have 2 black nodes to every path in the tree. Okay, so I have a question for you. So it's 10:56. What would you rather me do? Would you rather me go through examples of AVL and B tree insertions and deletions, or would you rather me walk through the process of how my B tree is designed in C++? The exam is on Wednesday, so I want to make sure that I'm devoting the right, basically what it is that you actually want to learn in this scenario. No one has a preference. Yes. Okay. Does anybody have? Would anybody be upset if we just continue doing examples instead of code? Okay. So let me hide this for a moment. So what would we? What tree do we want to do first? Any choice? Yes. Let's do an AVL tree. Okay, so we're going to do AVL. All right, so the key thing to remember about AVL trees is that this is the very first attempt at balance, and you learn some good fundamentals about how it is that we would want to obtain a perfect balance at any given moment. The drawback is that we have to keep track of the size at any given moment. As a result, it tends to take a lot more time, especially if you're building large things like databases. So first, I want to insert 10. And then I want you to notice here that in the animation, it has the height at any given time. So if I put in 11, we have, this is a balanced AVL tree because the difference is 1 and 0. So if I put in now, let's say I put in 16, then what's going to happen is it's going to get down here. And then at 11, it's a valid AVL subtree. And we're going to see the number change to 2. And the reason why it does is because that's still a valid subtree. It has 0 on the left and 1 on the right. But then when we move up here and it changes to 3, then we have 2 on the right and 0 on the left. So now what we're going to do is we are going to perform that rotation. And now we have a valid tree. The next scenario that I think is important for you to notice is if I'm going to insert 2 numbers. I'm going to insert 25. And when I insert 25, we're going to see that this is going to stay put. And the reason why is because it's going to be 1. When 16 gets evaluated, its height is 2, but its left side is 0 and its right side is 1. So that's a valid AVL subtree. And then when we move up here, it's going to be 3. And we're going to see that the height of the right subtree is 2 and the height of the left subtree is 1. So therefore, this is a valid AVL tree. So the number I'm going to pick next is 20. And this is going to evaluate a very specific scenario that we covered in lecture. So if we insert 20, Does anybody remember what this scenario, what we called this scenario? Yes. We had a zigzag, and then, so very good, we call this a zigzag scenario. And for an AVL tree specifically, what did we have? We had to do a very specific task in order to make sure it's balanced. So what did we call that task? Yes. Absolutely right. We have to do a double rotation. So in here, what's going to happen is it's going to evaluate. 25 is going to be fine. 3 is now going to be not fine. But if we just did a rotation where we had like so, what's going to happen is in order to make this work, we have to move 20 up. Does everybody see that? That was the double rotation portion. Because if we move 25 over, then we would be violating higher up the tree. So when we have a zigzag scenario, we move the middle up like that. And then we go up the rest of the tree, and we see that we have maintained our valid rotation. So now I'm going to insert to try to go over that case again. I'm going to do 13, and I'm going to put 13 here. And so when we go up, it's fine here. It's still going to be fine here, but now we're going to have a problem here. And this is where, on an exam, this is the scenario that will likely come up that you will have to do. So what we're going to do is we're going to move 16 up. So let me step back and describe why it is that I said so. The reason why we have to do this is so we have a double rotation. And here what's going to happen is in order to for this to be properly balanced, 16 needs to move up, 11 is going to become 16's left child, and 20 is going to become 16's right child. Everybody see that? The one thing that we have to remember is that 13 is still there, so we have to make 11's new right child become 13. And we know that's valid because 13 is greater than 11 but less than 16. So what we're going to see when we perform this final rotation is 16 is going to be here, then it's going to become 11, 20 will remain the same, 13 is going to be 11's right child, 10 is going to be 11's left child, and we're still going to have 25 over here. So I'm going to walk through the actual animation, and that is why that scenario occurs. So let's walk through a couple of deletions. Yes, so Fan Kong is absolutely right. That was a zigzag scenario. So first, I am going to delete 16. And so what's going to happen is 16, we're going to grab the largest value on the left-hand side, and we'll move it up. And then we would be checking where I deleted it from. So it turns out that every single subtree is valid. And the reason why every single subtree is valid is because there's no more than one difference at any given node. And so we are evaluating it at each level. So now what's going to happen is, let's say I choose to delete 20. If I choose to delete 20, then what's going to happen is nothing's on the left, so now it's going to grab the node on the right, like so. And we still have a valid tree. And the reason we have a valid tree is because, again, we have no greater than 1 at any given subtree. So now I can cause all kinds of trouble by deleting 25. If I delete 25, now I have 2 on the left and 0 on the right. So now this is a single right rotation. So here I would be moving 11 up, and 13 would become the right child of 11. Then if I delete the last 3, if I delete 11, we're going to move 10 up. And we still have a valid tree. If I delete 10, then I'd move 13 up. And then if I delete 13, then nothing would be left in the AVL tree. Does anybody have any questions about anything I just covered on that example? All right, so what would we like to do next? Okay, let me propose an idea. Just so we're all clear, I'm going to make this empty, and let's do a max heap. We're going to do insertions and deletions into a maximum heap. So I'm just going to come up with random numbers. So I'm going to do 19. So initially 19 would be here. If we're going to do a max heap, so let's do, I did 32. So 32 would initially be here, and then what would happen? Yep, very good. We're going to swap these up, right? 32 would become the top here, and then 19 would move down. So now if I put in 7 would initially go here. And so just to review, why is 7 going there? What is the underlying data structure of a max heap? Yes. You're absolutely right. It's a dynamic array. So what we're doing is we're pushing back onto a vector, and then we would be heapifying if it violated our case. So if we did 11, 11 would go here. And then let me put in 22. So what's going to happen here? Yes. Absolutely right. So 22 and 19 are going to get swapped. And so I'm going to put in 6, 3, 0, and then I'm going to put in 99. So I put in 99. What's the first step? Yes. It's got to swap with 11. Very good. So let's just erase that step by step so it's clear for when you're reviewing later. So we have 99 and 11. So now what's the next step? What's the next step of this approach? Someone new, give it a shot. Very good. So that is 22, so Tiani is correct. So we're going to move 99 up here, and we're going to put 22 there. So now what's the next step? It'll be relatively simple. What's our next step? Yes. Very good. Swap 32 and 99. Oh, meant to erase there. So Tiani is also correct. That is 32. So we're going to put 99 here and 32 here. So now let's say I want to pop off the top 2 elements. Okay. So here is how we would do this in an efficient manner. The first thing that we're going to do is we are going to get rid of that, and then we're going to take the last element in what would be the dynamic array representation and move it up. Okay, so in this case, that's 11. So we're going to move 11 up here, and then we're going to delete from there. Does everybody see that? So what is the next step? Yes. Yeah, we're going to swap with the greatest child. Very good. So the greatest child in this case is 32. So Brandon is also correct. So now we're going to move up 32 and we'll move 11 down here. So now what's the next step? We have one more step that we need to do before we have our complete answer for this deletion. What do you think we need to do here? I'll give you a hint. We are currently there. Let me see if I can give you a hint to the right answer. What is the main property of a maximum heap? So Fang Kong has said the right answer, but I want to see if I can show you all why it is that it's the right answer. So what is the main property of a maximum heap? Yes. Parents are always going to be greater than the children. So what is it? Why is this tree currently gone? And so Tiani has said it absolutely right. So where is this tree violated? Where's this heap violated? Yes. 11. Yes, absolutely right. Both of its children are greater than it. So if we're going to continue to move this down, what we're going to do is we're going to swap with the largest value. Here's a question. Why the largest? Yes. Absolutely right. So if I pick the largest one, then I'd be violating the condition. So what I want to do is I want to swap 22 and 11. And now since 11 is greater than 0, we now have that tree. So the last part is, what if I want to pop off this last one? So then just to kind of go through it pretty quickly, it would be 0. We'd move 0 up here like so. And then we would swap 0 and 22 and then 0 and 19. So this final heap would be as follows. This would be 22, 19, and 0. Does everybody see that? All right, last, a min heap is just the same thing in the opposite order. So we have 4 minutes left. So what I would like to do is now let's go to a B tree. And I'm going to select max degree of 4 for this problem. In this particular case, you can also enter strings up to 4. So if I say NOTR, that could be like Notre Dame. If I put in DAME, that moves over. And if I say beat, now that's going to be the third one over, right? Now, if I put in LOUI as in Louisville, what's going to happen is that would become the third element in that B tree, but it would overflow. So Dame is going to be moved up. And then beat is going to be on its left child, and Louisville and Notre Dame would be on the right. And who do we play next week? Pitt? Okay. And so now I'm going to add in, that works perfectly, Pitt. So now we're going to see that it goes in the right-hand side there. And then I don't know if you all remember this, but there's this famous NCAA tournament basketball game where Bradley played Pittsburgh, and on the score it said Brad Pitt at the top, and everybody thought that was funny. So I'm just going to put in Brad for Bradley, and it's going to move over here, and it's going to become on that right one there. So I know we also play Wake at some point. So Wake Forest would move over here and split everything. And then I'm going to put CLEM for Clemson. Clemson would fill that one up. And if I put in FSU for Florida State, that would go in the middle. And I'm just trying to pick other opponents. We'll do BC for Boston, BOST for Boston College. And so BO would go here, right? So it would go in the middle there, it'll split and go up like that. And so since we beat, I'll pick Florida State, since we beat them, we'll delete that, and we'll see that this is going to now leave it alone. Now, if I delete Louisville, since we also beat Louisville on Saturday, we are going to do that borrow from left. So what you're going to see is Dame is going to come down and Clemson will go up. I hope we don't repeat that in a few weeks, right? And now if I do the same thing, if we're going to delete Clemson, then we run into this scenario where we're going to move everything up. Oh, it's a little fast. Let me go back, skip back. So I'm going to pause and I'll walk through this, and this is a good thing to end on. So take Clemson out. And what's going to happen is we step forward and we would be rotating this up, but now we have that scenario where we don't have enough values to fill all those nodes. So we would be combining Brad and Dame, right? Actually, we'd be combining these three nodes with Boston, Brad, and Notre. And you're going to see that Boston is going to be moved down, and then Brad is going to become that portion. So let me step back. This is a good thing to end the lecture on. This is borrow. Boston's going to come down and combine with beat. So we're going to beat Boston College, and then it's going to move everything else over from the right, like so. Okay, does anybody have any other questions? Okay, on that note, I wish you all the best of luck in your studies. Those videos are available, and I will see you on Wednesday for the exam.